Hello, welcome to TA Instruments QuickStart e-training course for the ARES-G2 rheometer. I want to thank you for being a TA customer. Most likely, you are a new user or have recently purchased a rheometer from TA Instruments, and we really appreciate your business. This is one of a series of recorded courses designed to ensure that our customers get the maximum benefit out of their instrument equipment. This course is designed for new users of the ARES-G2 and the TRIO software used for instrument control and analysis. By the end of this course, our goal is to provide you with general operational knowledge and the confidence to work with the ARES-G2 instruments. If the ARES-G2 has not been installed, please refer to the ARES-G2 Getting Started Guide or contact a TA Instrument Service representative before proceeding. This course will cover the following topics: basic introduction to the ARES-G2 instrument, setup and operation of the ARES-G2 instrument hardware, introduction to the TRIO's control software, setting up the ARES-G2 for an experiment and running an experiment. We will show two different experiments using two different materials and temperature control unit. The first will be an oscillation frequency sweep measuring the viscoelastic properties of polydimethyl-siloxane, and the other will be a flow sweep test measuring the viscosity of a silicone oil standard. We will conclude by pointing out some common features used to view and present data within TRIOs. Before we move on to discussing the ARES-G2, let's talk in general about what does a rheometer do. A rheometer is an instrument that can measure both viscosity and viscoelasticity of a wide range of materials, including liquids, semi-solids, and solid. Viscosity is defined as a material's resistance to a flow deformation. Viscoelasticity is a property of a material that exhibits both viscous and elastic character. A rheometer works by relating a material's property of how hard it's being pushed to how far it moves. The ARES-G2 rheometer does this by commanding an angular displacement, which is the raw signal for strain, and then measuring the torque, which is the raw signal for stress. Let us start off by providing a basic introduction to the ARES-G2 instrument and highlight some of its hardware features. The ARES-G2 rheometer has a separate motor and transducer design. The motor is located on the bottom of the instrument and directly applies the strain deformation to the specimen. The force rebalance transducer, the FRT transducer, is located on the top and measures the torque response from the specimen. The modular power supply box is separated from the testing station. It helps isolate any vibration from the electronic supplies. Depending on what temperature control unit you have selected for your instrument, you will also see another smaller electronic box for environmental control. This box will stack above the main modular power supply. On the bottom of the ARES-G2 testing stage, there is a touch pad which is used for some basic instrument operations. On top of the instrument head, you can see a touch screen window which will also allow you to check on instrument status and perform some basic operations. Now let's talk about some basic instrument setups and operation. The ARES Getting Started Guide can provide detailed descriptions on basic instrument setup and operation of the ARES-G2 and numerous accessories. These guides are installed with the TRIO software and can be accessed by double-click on the ARES-G2 menu icon on the computer desktop or via the Start menu. Additional instructional information can also be found in the TRIO's software help manual, which we will discuss later. Usually, After TA service engineer install the ARES-G2 rheometer in your lab, there is no need to turn off the instrument on the daily basis. But if your instrument is currently powered off, here is a simple acronym for you to remember how to properly power on the instrument. AUP. A means air, U is unlock, and P is power. Following the Getting Started guide, first make sure the air is connected and set to 80 to 90 psi. Then unlock the motor and transducer. The third step is to turn the power on. Again, step 1, make sure the ARES-G2 is connected to a clean and dry air source regulated at 80 to 90 psi. Please note, attempting to operate the instrument when air is not connected can damage the instrument air bearings. Step 2. With the air supply on, it is now safe to unlock the motor and transducer. Remove the 4 screws to unlock the motor. Save all the screws and the locker piece for future instrument shutdown. To unlock the instrument transducer, pull and turn the locking handle towards the back of the instrument. Step 3. Now we're ready to power on the instrument. First, we need to power on the electronic boxes. The on and off power switch is located on the back of the electronic boxes. Make sure you turn on the power to the main power supply first, and then any other environmental system electronic boxes if needed. Finally, turn on the main power from the front instrument control panel. Do not touch either the motor or transducer. Wait for a few seconds until the instrument completes its self-initialization process. When the ARES-G2 has been powered on correctly and is ready to use, the front control panel on the bottom of the instrument will show green lights near the transducer, motor, and power buttons. And the top LCD screen will display basic parameters such as torque, axial force, and temperature. From the top LCD touch screen, press on the status button, check and make sure that the main air inlet, motor air bearing, and transducer air bearing are all within the green area. On the right LCD screen area, make sure under System Status, green lights are shown on all of the accessories you are about to use. Now the ARES-G2 instrument is ready to use. Now that we have introduced the ARES-G2 instrument hardware and have it powered on, we can go ahead and start the trios control and analysis software. In the next few slides, we will display the basic layout and features of the ARES-G2 software. All examples shown in this course were taken from Trios version 3.3. The current release version of Trios software is available to download for free from our website. Once installed, open Trios software by double-click on the icon located on the desktop or select from the Windows Start menu. The instrument view window will open. Select the ARES-G2 instrument and then press Connect. If an instrument-specific shortcut has been created on your desktop, the instrument view step may not be necessary. Once connected successfully, the software will open and look like this. Underneath the instrument icon, it should show Instrument Online. In this mode, the software can perform instrument control and data analysis at the same time. If the software is open without connecting to any instrument, it will show Offline. In the offline mode, the software will only be used for data analysis purpose. The Trio software is constructed with 4 major sections. On top is the main ribbon. This Trio's ribbon is context sensitive, meaning there will always be an array of relevant options displayed based on an active selection. One of the most useful features in the main ribbon under Experiment icon is to access the Trio's help menu. click on the big white question mark icon. Will open the Trios help menu in HTML format using the default web browser. It does not require internet access for viewing. Browse the content or utilize the search feature to locate in-depth instrumental information regarding the ARES-G2 hardware, software, and operation. Access to all Getting Started guide can also be found through this Trios help. Underneath the ribbon, there are 3 panels. On the left is the File Manager. On the right is the Control Panel. And the center part is the main working or display window. The File Manager panel has 4 different title bars on its bottom: Experiments, Results, Geometries, and Calibration. Trios will open by default in the Experiments view. It is in this window where all experimental parameters will be entered in the center working area. Clicking down to the Results bar, this is where results are viewed and data analysis is performed. Currently running experiment will be displayed in real time, and data previously collected can also be opened from this window. The Geometry bar displays a list of all geometries entered into Trios. Geometry information and their calibration can be accessed from this window. The Calibration bar is typically reserved for your service representative. It is used to access instrument calibration and advanced accessory setting informations. On the right-hand side of Trios is the Control Panel. When connected to an instrument, this panel will display by default. However, if not displayed, the Control Panel can be accessed by clicking on the Control button from the top Experiment ribbon. In the Control Panel, the real-time signals from the ARES-G2 are displayed just like on the instrument display. Below are several bars used to command specific instrument operation outside of a test procedure. These operation commands include gap, environmental, motor, transducer, and axial force. Utilize the help menu to become familiar with these operations, as they are important for both instrument and sample loading procedures. In the next section, we'll be talking about how to set up for running an experiment. There are 5 basic steps for setting up for an experiment. First, select a temperature control system and install. Then, select and install an appropriate geometry. 3. Set up the experimental parameters in Trios software. 4. Load and trim the sample. And finally, start the experiment. This slide shows the 2 most popularly used temperature control systems for the ARES-G2 users. The one on the left is the Advanced Peltier system. This temperature control unit can be used in combination with parallel plate, cone and plate, and concentric cylinder geometries. The operation temperature range is from -10 degrees up to 150 degrees Celsius. The picture on the right side is the forced convection oven, the FCO. The FCO oven provides the widest operation temperature window for the ARES-G2 user from -150 up to 600 degrees Celsius. Geometry that can be used with the FCO oven includes parallel plate, cone and plate, and torsional geometry. The advanced DMA mode geometries, such as tension, 3-point bending, and cantilever, are also used with FCO. Regarding installing the temperature control system, if the user purchased the ARES-G2 FCO oven, it should be pre-installed by a TA local service engineer and should already be ready to use. To install the Advanced Peltier system, the APS, the user needs to follow the ARES-G2 APS Getting Started guide. the APS Smart Swap temperature control will be automatically detected and configured when connected to the ARES-G2 port. Please note that a circulator is required when using the advanced Peltier for temperature control purpose. The next step is to select the most appropriate geometry for the measurement. This slide displayed 4 classes of geometries and the typical range of materials they are used to test. The concentric cylinder geometry is commonly used to measure low to medium viscosity liquid, any sample that can be loaded into a cup. The cone and plate and parallel plate geometries are most popularly used geometries for regular rheological measurements. The samples that can be measured varied from low viscosity liquids to cured solids. The torsional geometry is designed to measure medium to high modulus solid samples in cylindrical or rectangular shape. By selecting a correct geometry, one should be able to use the ARES-G2 rheometer to measure any sample with viscosity as low as water or any sample with modulus as high as stainless steel. Once the measurement geometry has been selected, one should follow the online help manual with detailed steps on inserting the platinum resistant thermometer, the PRT, and installing the upper and lower geometries. After the installation, go to TRIOS software. From the upper main ribbon, select the correct geometry that has been installed. For the FCO oven users, an appropriate gas source needs to be selected to purge into the oven for temperature control. For example, when testing a sample under subambient conditions, the liquid nitrogen source needs to be selected. When testing polymer melts, a dry nitrogen source, which showed as gas in the software, is commonly used to protect the sample from being oxidized during measurement. This function can be found from TRIOS control panel under the environmental bar. After the gas source is selected, the initial measurement temperature can also be entered from this page. Alternatively, FCO oven gas source and initial test temperature setup can also be performed using the upper LCD touch screen under the temperature control icon. At the measurement temperature, the zero-gap operation can be performed from either the upper instrument LCD screen or from the TRIOS control panel under the gap bar. The next step is to set up a test program in TRIOS software. Under the experiment view, 3 major bars will be seen in the major plotting area. First, the sample bar, which allows you to enter your file name, operator name, project details, and find a path to save your data file. Next, click down to the geometry bar. This area shows all of the information for the current selected active geometry. The third bar is the procedures bar. There are numerous procedures available within TRIOS. A single or multi-step test procedure can be created using the options from the drop-down list. In each step, the first drop-down window on the left side shows all of the available test modes and all operation conditioning settings. The most commonly used test modes are oscillation, flow, and step transient. Each test mode also includes multiple specific test procedures. For example, in flow mode, one can program a flow ramp test, a flow sweep test, or a flow temperature ramp test. The tables on the right side of this slide listed all of the test procedures that are available under flow, oscillation, and transient modes. Now we're ready to work through the basic steps for running an experiment. In this section, we're introducing testing 2 different types of samples in 2 different test modes. We will also use 2 types of temperature control systems with different geometries. The first sample we will be testing here is a viscoelastic polymer standard, polydimethylsiloxane. It is available and can be purchased from TA Instruments. We'll be using the forced convection oven with a pair of 25mm plates for this measurement. The test procedure is a dynamic frequency sweep at 30 degrees Celsius. At the end of the test, we will analyze the results by verifying the G crossover modulus and G crossover frequency. This kind of frequency sweep procedure is commonly used in polymer industries for evaluating the viscoelastic properties of polymers in their molten state. The measurement results are very sensitive to the polymer chain structure and entanglement. It can be used to evaluate polymers' molecular weight and molecular weight distribution. To test the PDMS, select oscillation mode and frequency. Set the temperature to be 30 degrees Celsius and soak time of 5 minutes. Make sure to check the box for wait for temperature, as it will command the temperature control system to first attend the measurement temperature before the soak time begins. Move down to test parameters and set the strain to be 5%. Please note that this amplitude has to be within the linear viscoelastic region of PDMS under the frequency range selected. Choose a logarithmic sweep of angular frequency between 1 and 100 radians per second and collecting 5 data points per decade. All settings below this point will remain at their default values. For instrument setup, follow the manual and install the 25mm upper and lower parallel plate geometries. Close the FCO oven. Set the measurement temperature to be 30 degrees C. After the geometry is equilibrated, zero the gap. Now we're ready to load the sample. Quickly open the oven. Load the sample between parallel plates. From the instrument control panel, press both the down and slew buttons to squeeze the sample down until it gets close to the target gap. Then use either the upper LCD screen or the TRIOS control panel to set the geometry gap at 1.05 mm. The trim gap offset is usually set to be 5 to 10% above the measurement gap. That means if the measurement gap is set to be 1 mm, then the trim gap offset should be 0.05 mm. Trim the access sample at the gap of 1.05 mm. Then close the FCO oven. Equilibrate the sample to 30 degrees C. Go to the final measurement gap at 1 mm. For a certain selected geometry and gap, the minimum required sample volume to fill the set gap is listed under the geometry bar. It is a helpful reference for a user to estimate how much sample is required. For a good sample loading and measurement, it is usually recommended to load approximately 10 to 20% access sample volume to allow for proper gap filling. When using parallel plate or cone plate geometries, be certain to verify the sample loading and inspect the sample edge. Improper gap filling or trimming can lead to experimental error, which is difficult to troubleshoot from the resultant data collected. Be sure to also monitor the sample for trapped air bubbles, evaporation, or material leaving the gap during testing. Now that the sample is loaded and the test parameters are set, we're ready to start the measurement. Go to TRIOS software, make a final check, and see if the sample information and the file name are correctly entered under the sample bar. Make sure you have selected the correct folder to save your data file. Do a final verification. Check and see if the correct geometry is selected and active in the geometry bar. Check and see if the frequency sweep procedures is programmed properly. Then start the test. Once the experiment has started, TRIOS will transfer this file to the results view, and the real-time data plot will be displayed in the center area of the software. Here, the default frequency sweep results will plot storage modulus, loss modulus, and complex viscosity as a function of angular frequency in log-log scale. The second sample we're testing here is a Newtonian silicon oil with a viscosity about 1000 centipoise at 25 degrees Celsius. This sample is also available and can be purchased from TA Instruments. We will demonstrate using the advanced Peltier system with a 50 mm 0.02 radians cone plate for the measurement. The test procedure is a steady-state flow sweep test under 25 degrees C. We will verify the viscosity of this oil at this specified temperature. This test method can be an example of analyzing viscosity property of most liquid samples. In this flow sweep experiment, we set the test temperature at 25 degrees C and let the sample equilibrate for 5 minutes. The flow sweep is from 0.1 reciprocal second to 100 reciprocal second with 5 data points per decade. In order to ensure that each data point is collected under equilibration, TRIOS requires the operator to enter an appropriate equilibration time and averaging time. A Newtonian fluid needs shorter time to reach equilibration. But for testing any non-Newtonian liquids, it usually requires much longer time for equilibration, such as 10 to 30 seconds. Follow the manual to install the advanced Peltier plate and 50 mm cone geometry. Confirm that the temperature has reached the set value of 25 degrees and is stable before zeroing the geometry gap. On the center of the plate, place a small portion of silicon oil, taking care not to introduce any air bubbles. Set the gap to the trim gap, and confirm there's enough sample to fill the gap. More oil may have to be added from the edge of the geometry if needed. When the gap is completely filled, trim the excess sample using a non-absorbent tool. Then go to the geometry gap and start the experiment. Again, TRIOS will open the results view and display the real-time data collected. The test results for the 1000 centipoise oil are shown here, plotted as viscosity and stress versus shear rate in log-log scale. At the end of the test, raise the instrument head, remove geometry, wipe off the sample, and clean thoroughly with water or ethanol. At TA Instruments, we typically recommend that you leave the instrument on all the time. However, if there is a need to turn off the instrument at the end of the day, then follow the instructions below. First, turn off the power from the instrument control panel. Then, turn off the power from the electronic boxes. If there is a need to turn off the air, lock the motor and transducer before the air is turned off. We have given a brief instruction to the basic structure of TRIOS software earlier. In this section, we will highlight a few methods to view, present, and analyze data within TRIOS. TRIOS is a software package which allows instrument control and data analysis at the same time. The experimental design and parameter setup are under the experimental page. The results view and data analysis is under the results page. When you open the data file, the file name will be listed under the results page. In the meantime, the upper TRIOS ribbon will display related functions for editing, formatting, and analyzing the tested results. Upon opening a data file, one should be able to view first the result data plot, second, the spreadsheet with all raw data in columns, and third, the original test setup parameters and geometry information. To change the parameter units in the results, click on the TRIOS icon from the top left corner, select Options, and then Units. All of the available plotting and analysis features can be found from the top TRIOS ribbon under Format, Edit, and Analysis icons. With a result file open, the default plot variables will be displayed. To change the selected plot variables, use the Select button under the top Edit ribbon. Alternatively, move the cursor over the plot area and just double-click or right-click the mouse. Then choose Select Variables. A Graph Variables window will pop up and allowing users to decide what variables to plot on the X or up to 4 y-axis. Plotting in trios allow more than one variables to be displayed on a single y-axis, as shown here for storage and loss modulus. Click OK to exit the window. Any changes can be saved as the default plot configuration. Future tests of the same experimental type will be displayed with the same saved layout. We will now look into plotting data from different files on a single graph using the overlay feature. Creating an overlay plot is a powerful data visualization tool that allows a quick comparison between different sample results. First, open all data files to be overlaid. Then, right-click and select New Overlay Document. A new overlay file will be created in the File Manager window, and the results view displays an empty plot. Simply click and highlight the file to be overlaid. Drag over to the plot area. An overlay plot of 2 PDMS frequency sweeps is shown in here. These results show perfect test reproducibility using the ARES-G2 rheometer. Alternatively, open one file in the plot area. Highlight the second file that needs to be overlaid. Right-click the mouse and select Send Data to Graph, or use the Send to Graph icon from the top toolbar. The overlay plot can now be edited and saved like any other files without compromising the original file layout. To apply an analysis function within trios, open a data file. Go to the top Analysis ribbon and select the desired analysis function from the drop-down list. In this case, we would like to analyze the modulus crossover frequency and crossover modulus. Highlight the data range to be analyzed and press the Analyze icon. Please note that certain analysis model may require a specific set of variables to be displayed. If the analysis is not active, utilize the Match button to adjust the plot variables according to the selected model. Here we have performed the modulus crossover analysis on the PDMS frequency sweep data. The G crossover modulus and frequency are displayed on the plot. Compare your measurement results with the value labeled on the PDMS bottle. If the error is within 5%, it means that your DHR instrument is working properly and your experiment was all correct. In addition to the analysis function list, the data at a specific point can be stamped to the plot by right-clicking on a selected point. Annotating the curve with statistical analysis is also possible. Highlight a range of data to analyze. Right-click and choose Stamp. The Annotate Curve with Statistics options will display the mean, standard deviation, relative standard deviation, and variance for the points highlighted. Here we have annotated the 1000 centipoise oil data with statistics. The silicon oil we measured is a Newtonian material. Therefore, the measured viscosity is constant and independent of shear rate. The average viscosity value closely matches the value listed on the bottle. At the end of this training, we would like to let you know that once you start working on a TA Instruments rheometer, you can always find support from us. Please feel free to reach out to the applications and service support hotlines via phone calls or emails if you have any questions. In addition, TA Instruments website also provide opportunities for registering other levels of training courses, attending pre-recorded webinars, viewing available TA tech tips, and downloading hundreds of applications note papers. Thank you very much for attending this ARES-G2 e-training course. We look forward to working with you more in the future.